Hello everyone, I'm Yiyong from CISPA, and it's my honor to share with you our recent work at SoK data reconstruction attacks against machine learning models, definition, metrics, and benchmark. Over the past decade, machine learning has seen significant advancements and has been widely adopted in real-world applications, including highly privacy-sensitive tasks such as personal identification, disease diagnosis, and financial risk assessment. Training a high-performance machine learning model demands a large volume of data. To prevent the leakage of the trained data, the model owner tends to release the model only. However, a series of works demonstrate that with only limited access to the model, the attacker is still capable of inferring partial and even complete information about the model's training samples. Those privacy attacks include membership inference, attribute inference, and property inference. The ultimate privacy breach is data reconstruction, as it exposes all information about every sample. Due to the crucial role of data reconstruction in the field of privacy, numerous attack methods have been proposed in recent years. However, a major problem in this area is the lack of a rigorous definition. This ambiguity largely stems from the diverse scenarios in which such attacks are applied, including different training types, different model accesses, and different dataset access to the target model. Based on these aspects, we provide a rigorous definition. To define data reconstruction, it is essential to clarify two key aspects: what information the adversary processes and what data they aim to reconstruct. We began by categorizing 10 representative reconstruction attacks based on the type of training, the level of access to the target model, and the availability of the dataset, all of which are considered forms of the adversary's actual knowledge. The adversary typically aims to reconstruct the data of the same scale as the original training dataset. It should be emphasized that generating more samples and selecting high-quality reconstructions is allowed, while this selection procedure should not involve any information about the target dataset. In addition to the lack of a clear definition, there is currently no consensus regarding appropriate metrics for attack evaluation. Visualization offers an intuitive and direct impression of reconstruction quality, but its subjective nature and lack of quantifiability limit its effectiveness. Common quantitative metrics such as MSE, PSNR, and SSIM are sensitive to the choice of sample pairs and do not reflect the diversity of the reconstructed data. Feature-based evaluation metrics are highly dependent on the choice of the evaluation network and also fall short in capturing reconstruction diversity. As for the accuracy-based metrics, we show that even visually noise-likely reconstructions can achieve high accuracy, indicating a mismatch between these metrics and the true perceptual or structural fidelity. And the same problem is with using testing accuracy as a metric. With a clear definition of data reconstruction, establishing robust evaluation metrics becomes equally critical. In light of the limitations of existing metrics, we propose a set of desirable properties that effective evaluation metrics should satisfy, including quantifiability, consistency, precision, and diversity. To address these requirements, we first introduce a dataset level metric that assesses reconstruction quality from a macro perspective. Specifically, we adopt the FID to measure the distributional similarity between the reconstructed dataset and the targeted dataset. FID is model agnostic and can be computed using various feature extractors, offering both consistency and quantitative comparability. In addition, we introduce our set of sample level metrics focused on both precision and diversity. These metrics evaluate how closely each reconstructed sample aligns with its corresponding target sample, rather than assessing only the overall distribution. The selection of the similarity function D is flexible and can be tailored to the specific aspect of reconstruction quality being evaluated. Furthermore, the inclusion of the coverage alpha rate alpha serves as a crucial complement. providing a more comprehensive view of reconstruction performance. To ensure a comprehensive evaluation, we train the target model on subsets of varying sizes, ranging from 100 to 20,000 samples. Both the training and the auxiliary datasets are balanced to eliminate bias from classes. We begin by visualizing the reconstruction results of all 10 evaluated attacks. Among them, the three generative model-based methods, i.e., Revealer, KDMI, and PageMI, appear to produce reconstructions of relatively higher visual quality. However, none of these methods are capable of achieving exact reconstructions of the original data, and the quality of the reconstructed samples varies significantly. To better analyze and compare these attacks, we apply the proposed metrics to evaluate the reconstruction datasets, and you can find the complete results in our paper. We can first focus on the results with the largest training size, and it confirms that GAN-based attacks outperform other methods with their consistent lower FID scores, which is aligned with the visualizations. However, relying solely on FID may not fully capture reconstruction quality. For example, as for the Salaba dataset, if alignment generates reconstructions that clearly show the semantic meaning of the target dataset, i.e., human faces, whereas some deep inversion reconstructions lack sufficient information, despite having a lower FID score compared to alignment. As a comparison, the results with three sample level measures are consistent with our expectations. Sample level measures also provide assessment on diversity. We found that high quality reconstructions do not necessarily imply high diversity among the reconstructed data. Additionally, we observe a decline in coverage as the size of the training dataset increases. This trend supports our hypothesis that current reconstruction attacks tend to capture general information in the training data rather than reconstructing individual samples in detail. Observed results from sample level and dataset level metrics are generally aligned. There exist distinctions between them. Dataset level metrics offer a macro level view by evaluating the global similarity between data distributions, while sample level metrics provide fine-grained insights into the fidelity and the variability of individual reconstructions. Therefore, employing a combination of both types of metrics is essential for a comprehensive and reliable evaluation. We observe that existing attacks show varying performance, and even the same attack may explore different levels of vulnerabilities when target models are trained with datasets of varying sizes. From the perspective of model owners, understanding which models are more vulnerable to data reconstruction attacks is essential. Previous works demonstrate a close connection between memorization and some types of parser attacks, such as membership inference, as data reconstruction can be framed as a search problem within the context of membership inference. We want to investigate whether models with higher memorization scores are more prone to data reconstruction attacks. We adopted a way to calculate the model memorization with the level 1 out change in the label. Just as expected, we observe that the model memorization score decreases as the training size increases. However, the performance of different attacks is inconsistent. We attribute this discrepancy to two potential factors. First, the attack methods may lack the necessary capacity to accurately capture underlying vulnerabilities, particularly in the case of non-generative model-based attacks. And second, the evaluation metrics used may not effectively capture the true performance of these attacks. As discussed before, while existing metrics provide a rough estimate of reconstruction quality, there remains a gap between the numerical results and human perception. In some cases, measurements do not align with visual evaluations. We admit that human inspection remains the most direct and intuitive method for quality assessment. However, it is often prohibitive in terms of cost and scale for extensive datasets. Therefore, to achieve an efficient and scalable evaluation, we propose utilizing GPT-4o. This model is recognized for its robust performance and has been further refined during the reinforcement learning from human feedback phase to align with human preference. In the May experiments, we have 6 versions of target models with varying sizes of the training data. Thus, we input all the 7 images, the original and its 6 reconstructions together into GP4 and get the response. Finally, we compute 3 numeric metrics to assess the performance. Although with some variability, the general trend is that reconstruction quality diminishes as the memorization score decreases. Visual evidence further supports the observation that reconstruction from the smallest target data size, that is 1,000 samples, resemble the target images more closely than those from the larger size, 20,000 samples. This observation aligns with our expectations, but contrasts with the results from previous metrics. We interpret these findings in 2 ways. From the perspective of game-based attacks, these methods reconstruct data at a class level and aim to closely approximate the distribution of the targets. Consequently, when a target dataset includes multiple samples within a class, achieving a close match for any specific target sample becomes unlikely. Conversely, smaller target datasets result in less generalized features learning, manifesting as blurred areas in reconstructions, like eyes and cheeks. While this blurriness negatively impacts performance as measured by both dataset level and sample level metric, its effect on visual assessments is relatively modest, provided the blurring is not extensive. The second interpretation brings forth another noteworthy observation. For each attack method, the optimal performance is achieved at a dataset size of 1,000. Interestingly, the second best performance does not occur at a slightly larger size, such as 2,000, but frequently occurs at medium data sizes, such as 5,000 or 10,000 samples. This suggests that the reconstruction process benefits from the model's ability to learn additional features. However, this advantage is counterbalanced by the challenges posed by larger datasets, as a more extensive training dataset complicates the accurate recovery of individual samples, consistent with our early findings. To further explore the benefits of feature learning, we trained a model pre-trained on disjoint datasets and fine-tuned it with the target data. This approach enables model to learn additional features as evidenced by the improved testing accuracy. The results indicate that pre-training enhances the advantage of using a smaller dataset size, as a pre-trained model has already developed a degree of generability and is able to learn sample-specific features more efficiently. In addition, we also provide more discussions from various aspects. We found that the low-quality reconstruction methods fail to exploit critical attack information. Some certain attack methods cannot fully leverage the model internal information. Memorization plays a critical role in determining vulnerability to reconstruction in the text domain as well. And we also give the directions for designing attack and defense strategies in the future. You can find all the details and results in our paper. Thanks for listening and welcome to use our framework.